Welcome to the Inside EVs podcast and the second edition of a very special 10-part series going deep into the technology behind the move towards electrification with our partners at AVL. And we love to talk to the experts at AVL about the various issues and subjects around electrification, as it's their business to work with not only many OEMs but startups and companies of all shapes and sizes around the world as they move to e-mobility. If you missed part one of our series, I highly recommend you go back and listen to that one as well, as we looked back at the various paths towards electrification and asking, is there one solution that suits everybody, or maybe there's going to be a variety of different solutions of electric vehicles? Well, that was our first part, and I think you're going to like part two. Today, we're joined by Oliver Knaus from AVL. Oliver, welcome to the podcast. Give us a quick background of what you do, your job title, and what that involves.
Yes, thank you. My name is Oliver Knaus, and I'm skill team leader for the solution management team here in AVL for the division which is developing simulation software. And I'm responsible here for the portfolio of our software products. From my history, I started as a software development engineer, changed then to the application team, was a calculation engineer and project leader, and changed later on to the service group, was then responsible for customer support and software services. And then finally I moved into the product development and solution management team.
Now, we'll come on to software and electric vehicles a little bit later because the two are joining up quite nicely. But we want to talk about EV simulation. How would you define and what do you mean by simulation?
Yeah, we see a simulation more or less the numerical analysis of technical issues. And here we differentiate between system simulation and component simulation. So in case of system simulation, we are investigating mainly the functional behavior of such systems. And the systems have a level of complexity which you not just simply can calculate by analytical equations, but you need really to have a solver technology, and you investigate systems over a longer time frame. When we look at component simulation, then it's mainly 3D analysis of such system in a virtual environment and getting a deep insight of the behavior of these components when they do not still exist in hardware. So when you only have a CAD design and you want to understand how these components behave, then we apply our component simulation on it and get then result quantity in the direction of durability, of NVH behavior, thermal behavior, but also in case of automotive, also with respect to emissions.
So when we talk about simulation with electric vehicles, is this simulating parts that have already been made and then trying to develop them, or before you even get into the factory and you ever make a piece for a car, is that what you use simulation for? So, at the very beginning, or maybe it's a mixture of both?
It's a mixture of both. So when we think about the development process of an vehicle and a powertrain, then we are always talking about this V-type process, where we have on the left side the design process. And here in this design process, we are supporting the design by defining parameters, optimizing parameters, virtually validating the function and proper working of these components. This for sure happens before we have hardware parts of the components. When we think about the right side of the V process, then we have already hardware parts available. And then with simulation, we are supporting the integration tests, we are supporting the calibration processes, and we are supporting also to set up test plans for the hardware components. So here we have then a kind of a supporting function for the hardware testing and calibration.
Is it only a cost thing that we need to simulate? So from my naive perspective, simulation equals saving money. Is that correct? But does simulation have other uses apart from simply cost saving?
Cost saving is only one aspect of the whole story. It starts already very early as I said, when there are no hardware parts available, you are not able to test. So to optimize the design, the parameters, you need already simulation really during the design process on one hand. The other aspect for sure is also verification and validation in an earlier phase. So to shorten the development time to market, to have a product ready is under such a high time pressure that nowadays it's necessary to put things which you tested in the past, you have to put them in a much earlier phase of the process to be already very convinced that your design is working properly. Only the final validation, the final adjustment then should happen with the real hardware components. And then it's really just a verification loop because you want to avoid design loops to come then back after failures of tests and you have to redesign things. So it's really compressing the time frame and have the product ready much earlier. And the third part is that using simulation, you have the capability that basically you have an infinite number of sensors. So you can look into points and into positions of the design where you are not even able to measure things. If you have hardware components, you can add to this hardware a limited number of sensors. You can measure temperatures, you can measure maybe deflections. But by each sensor which you apply, you will maybe also influence the function of the component. And this you can avoid completely by simulation. You can extract results which you cannot measure, and you can measure more or less in a virtual case by simulation an infinite number of measurement points.
I think that's a really good basis on which to continue the interview so that I now fully understand what it's, when you say car makers or any company, component makers are under a lot of time pressure. That's true because people like me, EV fans, just want great cars now. And whilst there are many cars on the road and lots of vehicles coming, we always want more. We always want, more EVs. When it comes to the powertrain, from an AVL perspective or from an engineer's perspective, what does that define? What parts does that cover?
From AVL's point of view and definition, when we talk about powertrain, then we summarize together all the parts of a vehicle which are responsible for the propulsion of the system. But this is then not only the combustion engine, the e-motor, but also the drive shaft system, the transmission. It's also the charging, it's the battery pack which is providing the energy. It's a fuel tank. Or it's the power electronic which is responsible, the inverter, the charger infrastructure, the DC-DC converter. And finally, also the cooling system, because the powertrain will not work without the proper cooling. So also the cooling system, the heat exchangers, all these parts are also responsible for the propulsion system and therefore part of the powertrain as we understand it.
Does the software come into the powertrain, or would you define that differently?
We also count the control units because in a modern powertrain, the different components will not work without the proper control functions. So for sure, it's a battery management system, it's a hybrid control unit, it's a current control system. So all these control units have to interact with the physical components, and therefore also these control units we add as a part of the powertrain system.
Oh, that's interesting. So what are the similarities and maybe the differences between EVs and a traditional combustion powertrain that everyone's been expert on for decades, and it's been developing and developing. The electrified powertrains are relatively new. What are the similarities and what are the differences between the two?
Yeah, the similarities for sure is the vehicle itself and the requirements from the outside. When we develop a new vehicle, then we are looking at the vehicle attributes. We are thinking about the usage of the vehicle category, and from the basic expectations, they are very similar. When we go deeper, for sure, then we have the different components available. And here we see, especially in the engineering work, a major differences. On the classical powertrain, for sure, there was a lot of experience available. A lot of decisions were done and could be done based on the experience we had, an evolution of the individual development steps. Now, when it comes to EVs with the new components, engineers worldwide are lacking of this experience. There are not decades of experience where you know all the issues which can happen. And this is a major changes, which also makes then simulation so important, because you need to have a proper basis on which you can do your design decisions, on which you can optimize the system. And if you have not in the background this large amount of experience, you have to rely on virtual simulation, and for sure then later on proper testing under realistic conditions.
What kind of companies are your simulation tools aimed at? What sort of industries or companies, without naming names?
Yeah, basically, we are active worldwide in the whole automotive industry. So I would say there are not very, or there are very few companies where we are not working together. And we are more or less having three different groups of customers with whom we are working together. On one, these are the classical OEMs. And they are in a transition phase. So they have classically developed their conventional powertrains, their conventional vehicle, and they are in a transition to hybrid vehicle, to battery electric vehicle. And we are supporting them and moving on with them during this phase of transition. The second group are the startups. So we see that especially with battery electric vehicle, but also with fuel cell technology, there are a lot of new companies coming up. And they are even not coming from the automotive industry. So we have acting as a partner for them to help them to get introduced into the automotive industry, to understand the issues and demands which are related to powertrains and vehicle. And we help them also to learn how to develop such a complex product within a development process in the right way and in the very efficient way. And then the third group are the suppliers. And also here we see on one hand the classical suppliers who change their product portfolio to support also components from the electrified powertrains, companies who produced in the past pistons and cone rods and things like that. And they are moving and producing now battery packs and supporting the industry with electrified components. And on the other hand, we see also here startups coming for complete new technology. So very strong growing activities in the battery development, fuel cell stack development, fuel cell auxiliary components. So this is the third group of suppliers, and also due to the transformation of the industry, they have very specific demands and a strong learning process.
Let's talk about the various stages of making an electrified vehicle. I'll use a historical example now so that we're not talking about anything current. Many years ago when Tesla first started, for instance, they went to another company which was Lotus and got some cars from them, and they thought they were just going to put an electrified powertrain into the existing Lotus Elise and it would be easy, and then off they go. And they found out along the way, actually, we need to make this bit stronger, that bit lighter, this doesn't... They had to kind of almost redesign the whole car, so that then they ended up designing their own cars. That's a historical example of sort of 10 plus years ago. But clearly, you can't, it's not easy, is what I'm trying to say, to just take an existing car that is made either by yourself or by someone else and pop an electric powertrain in and put it on sale. Equally, it seems so difficult to sit down with a blank sheet of paper and say, okay, right, we're going to make an electrified vehicle. We'll start with a battery and we need a So What are the various stages of making an EV for different ways of doing it? And those stages of developing an EV, how do they progress from the concept to when it finally arrives in a customer's driveway?
Yeah, this is an question which there is not a one answer available, because it again depends who is doing it. When we see the classical OEMs who have vehicles available, for sure they intend and try to use their existing platforms and convert their existing vehicle platforms from a conventional powertrain to an EV, which is for sure a compromise. For cost reasons, for sure they intend to use the existing platform. They have a production plant and it generates less costs and more flexibility for them to go with this. From the technical point of view, for sure, it's a compromise, because the whole vehicle chassis and body structure is not designed to carry a heavy battery pack. It's not designed to have the main propulsion system with an e-axle on the rear axle. Most of the designs are done to support a front axle driving system. So it's then quite of a compromise. For sure, we see it completely different with the startups. They start from scratch, and for them, it's for sure reasonable and the best approach to design from scratch a new vehicle chassis and to work with this. And what we also see is that this is supported also with new technologies, with rapid prototyping technologies, that you have a chance now also with a smaller size of vehicle numbers, that you can very well produce a complete new concept and a new platform. But nevertheless, setting up a complete new vehicle platform also has then some other challenges. It's not only to set up a proper technical platform to drive the vehicle, but we also need to think about safety issues, crash testing and things like that, which are necessary and have to properly be designed for a complete new platform.
My goodness, I hadn't even considered something like crash testing. Can you simulate that before you ever crash a real car, which is expensive? Can you do all the simulation work on that as well?
Yeah, of course, has to be simulated for a proper design. So each of the we call it body in white structure needs to be properly designed to consume enough energy in case of crash. And it's not only to protect the people in the passenger compartment. When we talk about EV, then it's also a major topic here to investigate during crash simulation, the battery pack. So is the battery pack deformed? What effect has it on the battery modules inside of the battery cells? And will it generate then a damage of the cell, which leads finally to a thermal runaway, to an venting, and finally a complete hazard of the battery pack? So these things are already simulated and analyzed during the design process.
As an engineer, it must feel good for you when you do all that simulation and predict a certain outcome, and then when they finally do it in real life and it matches up. That must feel good when you can almost say, well, we told you so. We look at the result.
Yeah, this is always then a good point to have a proper validation and confirmation that what you designed, what you expected will happen, that you have then the confirmation about this. But nevertheless, it's also for such new things a learning process, because some parts you predict, and then it's also a learning process to understand what additional issue can appear. And out of this, we learn then again what other results we have to investigate, what other use cases have to be put into the simulation to cover all the different things which can happen in real life.
Okay, let's talk a little bit about the EV industry. How do you understand what the market needs So today, so your telephone rings and it's a customer and they want to talk about your help today. But also, how do you then predict what phone calls you're going to get in 5 years or 10 years time, so that when the phone rings in 5 years, you're able to say, "Yep, we've got the tools for that as well." How do you look forward, and how do you predict about what the EVs will be like in the future?
Yeah, this is what we call this attribute engineering. So based on this, we are very strongly thinking and designing the vehicle according to the customer needs. As I said, we are classifying the vehicles in different categories, in passenger cars, in sport cars, in luxury cars. And based on this, we try to understand what is the customer behavior. We support this with benchmarking of existing vehicles to drive this back to vehicle attributes and to understand why certain customers like one behavior or doesn't like the other behavior. And we see then how the demands of the customer is changing from a very end user's point of view. So what is the expectation in full deceleration? What is the expectation also from the packaging point of view, from the space requirement? So all this is defined, and we try to put this in objective attributes of the vehicle. And with this, we have a quite good way when we look at the history, at the current demands, that we can extrapolate what will be expected in some years. For sure, the industry is at the moment changing a lot, so also the consumer demands are changing, and this is why we have additionally the need that we are very fast. So when we see there is a certain customer demands, then we have to develop the products quick to bring it fast into the market. When you're talking about 5 to 10 years, we see that this becomes more and more difficult. So it's necessary to be here much more flexible, to be faster, bring the products faster into the market, because the demands and requirements are changing much faster than we have seen it in the past.
Can you talk a little bit about components being interdependent? So let me explain what I mean about that. In my old car, if I turned the heater on, there was a resistive heating element and it would heat up the cabin. In my electric car, which has a heat pump, so if I turn the heater on for the cabin because I'm feeling a little bit chilly, I'm aware that it's then affecting other parts of the car because it's scavenging heat from, I don't know, maybe the battery or the powertrain. I don't know enough about it, but I'm aware that to keep me warm, it's affecting other parts of the car. So I guess in an EV, there's lots of bits that are kind of interdependent. And if you don't fully understand that relationship between all the parts, that could be a problem. So with simulation, I'm guessing it's easier to model those interdependencies and the effects that various parts have on the car. But is that more of a case with electric vehicles than perhaps combustion cars, or not?
Yeah, this is much stronger in the meantime. So you're absolutely right. In a classical vehicle where we had the IC engine in, the cross influence between propulsion system, IC engine, and for example, heating and HVAC system was more or less the startup phase of the IC engine, and how long it took that the IC engine could provide enough power loss and heat to heat up in winter the car. But this was one of the strongest dependency. With electrical vehicle, this is completely different now, because the battery pack, the components in an EV are working in a complete different temperature range. And on the other hand, they are providing far not that amount of loss energy as heat source for the heating. So, and therefore we have a quite stronger cross influencing, and we need to have a much more complex cooling and heating system. So we also for heating need to have a heat pump system to heat up the passenger compartment very efficiently, similar like we do with the cooling. So this is only one interaction. The other interaction which we see is then backward. So the temperature of the components are strongly influencing the efficiency of the powertrain components. So a battery pack performance and efficiency is strongly depending on the operational temperature, which makes the system then more complex and also requires under cold condition that we need actively to heat up the battery pack to have it much more properly working. In a similar, it's also for inverter, for e-motor. So all the electrified components have a much stronger temperature dependency like we are used historically from the IC engine.
Presumably, that does come in terms of simulating these kind of interdependent parts. That seems, now I'm understanding, absolutely crucial to simulate that.
Yeah, and especially this feeds then also back and reflects in the simulation tool itself. So historically, it was okay if you had a simulation tool which only took care about vehicle performance, another one which considered for IC engine thermodynamics, a separate one which took care about the cooling and heating system. This is not possible anymore. So you have to put all these things also in the simulation environment together and simulate it together in one simulation run. And this is why the new simulation tools are more in the direction of multi-physics, multi-domain simulation to have all these cross influences together. So like the powertrains, like the vehicles are in a transition phase, we saw the same also on the simulation tool side, that also we had to do a transition to support these demands and to be prepared for these engineering tasks.
So the final question, as we approach the end of the interview, the final question I was thinking about is perhaps a topical one. Over the last few months, we're recording this halfway through the year 2020. We've had the global pandemic, and I've been following the progress of lots of exciting EVs that are going to be hitting the market very soon, and various car makers have been talking about how they've had to cope. Other car makers, though, have delayed their car launches because they haven't been able to test their cars. So over this period that we've just lived through, where people have been working from home or working remotely, could all of that development of those electric cars, or would some of that development have been done, would that have gone to more simulation, as people couldn't have got to, to actually make physical parts?
Yeah, we see due to this actual situation a strong move into virtualization. This was already in the past with the supporting design process. For sure, here the methods were established. What we see now is especially supporting the testing, supporting the calibration work of the control units with a strong push into virtual environments. So with our virtual calibration environment, with our eSuite environment, we are able to support this much stronger, with also the capability to have remote success. So it's not only that the process, the tasks are done more in the virtual environment, but also the working environment itself changed. So people are working much more remotely, and this brings also a stronger acceptance to cloud solutions, to cloud simulations, and the infrastructure. From the tool side, more and more web-based applications, remote access applications, big data analysis structure, all these things are much stronger demanded in the meantime. And this especially got a special push due to this pandemic situation and home office environments, which made a huge change in the mindset and in the working habits of the engineers.
And surely that must mean that you can attract, the days of, if I wanted to go work for a Californian company moving to California, or a Chinese EV maker having to move to China. I mean, that must mean for startups or anybody wanting to make a vehicle or an electric plane or boat that you can attract the best talent, the best people, and they haven't necessarily got to move halfway around the world to work from a certain office.
That's absolutely true. So we learned to team up, to build virtual groups which are located on different places. It's really exciting to see how properly this was working finally, much better than everyone would have expected upfront.
Wow, that is fascinating. Before you go, you mentioned at the very beginning your background is in software, and it's one of the most exciting parts of electric vehicles, I find, because I do, no disrespect to any particular car maker, but I always thought the software in all the cars that I've owned over the years, the software was never the thing that I got very excited about. It was either the performance or the engine, or, the software was there to do a function, and it did it well. Maybe it was for the radio or the HVAC system, but it wasn't very exciting. With EVs, and maybe it's because I'm a little nerdy, I love to be able to look at my phone, for instance, and I can see the state of my battery. I can heat up the car, or I can cool down the car from my mobile phone. I can start charge and stop charge. I can schedule things. And even when I'm in the car, the software does so much more than any of the previous cars that I've owned. How does that sort of simulation environment of trying to run everything through a computer before you even get to it, does that software side play an important part in the simulation, or is that separate?
No, this for sure is a strong topic also in the simulation side. We are not only developing and supporting the development of hardware components. In very strong increasing part is the function development, how we call it. So it's really taking the individual functional parts, and they are mainly representing by the software which is running in the vehicle. And it's, as you mentioned before, it's supporting capabilities of the powertrain, but it's also a driver assistance system. It's functions like ESP, torque vectoring. But when we think about an EV, there are also functions available which are supporting predicting the driving range, which is then connected together already in the meantime with the navigation system. So the system knows where you like to drive. The system double checks all the time under the current traffic conditions. Will you reach your destination, or do you need to recharge somewhere in between? It will suggest special routes which are supporting you in the right way for recharging station, or also it will explain you how you change maybe some settings or temperature or air conditioning, that you then be able to really reach safely your destination. Things like that are checked in the system, and for sure to develop these things in a proper way, it's upfront done in the virtual environment, it's upfront done by simulation and supported, that it's finally proper working when it's built in the vehicle itself.
Well, that's just absolutely fascinating, and I've learned a huge amount during this interview. I hope our listeners and readers of InsideEVs.com have enjoyed it as well. I sense from just the way you talk that you seem very excited about where this industry, as we electrify over the next 5, 10, 20 years, you seem excited about where it's going.
Yes, it's an exciting time for an engineers in a phase of transmission. We really like all the challenges, and it's for us a great experience and a pleasure to work together and to be partner with the automotive industry, with the OEMs, with the tier ones, to go together into the future. Yeah, it's exciting.
Oliver, thank you so much for your time today.
It was a pleasure. Thank you.
Well, that was a fascinating look at the intricacies of making an electric vehicle, and it's only part 2 in our 10-part series of Tech Talks with the team at AVL and brought to you by Inside EVs. Find out more, go to avl.com/electrification. That's avl.com/electrification. Check out part 1 if you haven't heard it yet from last week, and make sure you tune in for part 3 next week.